Okay, so the outline is I'm going to start with an introduction of fusion for those of you who are not familiar with it. And then I'll describe how magnetic geometries are devised in order to bring us closer to the goal of fusion. And one of the big issues that arises when doing this is magnetic islands. And so I'll describe the efforts to develop a predictive theory of magnetic islands that will make fusion possible. And there are basically one of the results, the basic result of that theory is that there are two types of magnetic islands that I call suppressed islands and fulfilled islands. The fulfilled islands, as their name indicates, are bigger and happier, but they're not good for fusion, so you want to avoid them. Okay, so magnetic confinement. The reason for fusion, of course, is that, as this diagram indicates, energy is extremely important to our well-being. What this diagram shows is that the gross domestic product per capita in a variety of countries is directly proportional to the amount of energy that's expended per capita. So basically, if you want people to produce a lot of wealth, a lot of goods, you have to give them a lot of energy to do it with. And it's possible to divert a little bit from that. As you can see, Japan is a little bit better at producing value with less energy, and then of course you have countries that are very oil-rich, like Russia and the Middle East, where they're a little bit less good at producing. But by and large, the path towards less poverty is more energy. Okay. So the way fusion works and how does it differ from fission? Fission you're all familiar with. You take uranium or plutonium, hit it with neutrons, and it splits up. And the problem with it is that when it splits up, it creates more neutrons, and so there is the well-known potential for a runaway reaction. Fusion is in a way, it's the opposite reaction. You start with very small nuclei, and you make them hit each other, turn into a bigger nucleus of helium. And there's one neutron that comes out, but the neutron doesn't participate in the reaction. So there's no possibility for a runaway reaction, and it's, because of that, inherently safer. The energy is much lower, but you have to compare that to the weight of the fuel that's being used. So in fact, in terms of energy per weight of fuel, fusion is much more, produces a lot more energy. And the nature of the fuel is also important. You can see the fuel is deuterium and tritium, which are isotopes of hydrogen. Deuterium can be mined from seawater, and tritium can be created from lithium, which can also be obtained from seawater. So the fuel is essentially unlimited, unlike fission. So the challenge, however, is that in the fission case, the reactants are neutral. In the fusion case, they're charged. And so you need to get these oppositely charged reactants to come close together enough to react. And it turns out that to do that, you need to heat, to energize your particle to 10 kiloelectron volts, roughly. That's the point where the reactivity becomes large enough. And that's very hard to do. The research on fusion started right after World War II, basically, and so we're 80 years later or something, and still working on it. So it's a very difficult thing to achieve. So there's 3 ways to make fusion work, and the nature's way is shown all the way here at the right. It's our sun, and in that case, the plasma, these highly energetic particles, are held together by the force of gravity. But of course, we can't have that much gravity to hold the plasma here on Earth, so that's not a practical approach. And the other 2 practical approaches that have been pursued are so-called magnetic fusion, where you hold the reacting plasma with magnetic fields, and inertial fusion, where really, in a way, you don't hold it at all. you illuminate a little pellet that's about this big of fuel with very powerful lasers. The latest iteration of this, I think they had 160 lasers or something like that. And all of these lasers cause the pellet to implode and compress to very, very high densities and temperature. And that's, okay, that's what's shown in this middle picture there. So that's the little white sphere is the pellet, the little blue rays are all the laser beams coming in, and the little cylinder is called a Hohlraum. It's meant to concentrate and make the laser beams more homogeneous. Okay. So there's another application I want to mention for confining plasma than magnetic fusion, and that's in keeping atmospheres around planets. We're fortunate to live on the Earth where we have a very nice atmosphere that we're working hard to mess up, but it's still very nice. If you compare to planets that don't have a magnetic field, such as Venus, on Venus, the only magnetic field is created by the inflow of the solar wind. And so the solar wind sort of creates a bow wave in front of Venus, but basically sweeping away the little atmosphere that Venus has. And in particular, water. So if you look at what's being eroded from Venus, you can see that the ratio of hydrogen to oxygen is about a factor of 2, showing that there's a lot of water being stripped away, and what remains is a sulfuric acid, so it's not a very nice place to live. So how do you do magnetic confinement? So there's several different approaches. The first thing one might think of is called the magnetic pinch, and that relies on the fact that, okay, the particles have a tendency, the Lorentz force causes particles to gyrate in very tight orbits around magnetic field. So the particles are it's as if they were tied to a magnetic field. But if the magnetic field intensity goes up, the magnetic moment has to be conserved. It's an adiabatic invariant. And so if the B field increases, then the perpendicular velocity increases, but the total kinetic energy has to stay the same. So at some point, the parallel velocity vanishes, and the particles are turned back. They just mirror from the region of high field here and go back. The problem is that that only works if the particle has low enough parallel velocity. If the particle is going perfectly along or very close to perfectly along the field line, it's going to be lost. And so you're constantly losing particles in that way. And it turns out that that's not a very promising approach. It's still being pursued by trying to plug the holes with the leaks with RF fields, but that's become a very small effort. Okay, so the next idea is, hey, since we don't want to have end losses, so we're going to curl the magnetic field and make it bite its own tail, and that way the particles will be lost. So you have now a system with closed field lines that make circles that are created, for example, by a current going down or up this rod here in the middle. And the problem with that is that the curvature of the particles as they're going around the magnetic field is proportional to the magnetic field. It's the magnetic field that makes them turn. So when they get closer to the current, the conductor over here, the magnetic field is stronger and their radius of curvature becomes smaller. So you can see right away that if they have a small radius of curvature on the right here and a big radius of curvature on the left, they're going to start drifting. And that's what you see. There's this sort of coil going up. So all the particles in an inhomogeneous magnetic field drift perpendicular to the gradient of the magnetic field. And so you're going to lose all your particles. And that drift is sufficiently fast that it doesn't allow for suitable confinement. So the next idea then is, let's wrap the field lines around a ring. And what happens if you do that is that this drift that I was just telling you about, okay, so the magnetic, so this is a ring of plasma. It has a symmetry axis that's over here, and so the magnetic field is stronger over here. That leads to this drift that I just showed you on the previous slide. But you can see that as the particles are going around these circles, they start drifting towards the bottom in the first half, and then when they get to the second half, they're actually drifting back towards the magnetic surface that they started from. Okay, so on average, their drift is 0. So what that shows is as long as you can have the field lines not just close upon themselves, but twist around a ring-shaped surface, then the drift can be 0 and you've got good confinement. Okay, so now the question then is how can you get this rotational transform? How can you get the field line to wrap itself around a ring? And there's two ways. One way is through plasma current. You actually have a current run into the board through the plasma, and that way has led to one magnetic confinement concept called the tokamak that I'll talk about. And the other way is if you twist the ring into a funny 3D shape, it turns out that you can force the field lines to also wrap around flux surfaces. So it's important when you're doing that, when you're designing your magnetic surface, the thing that you really want to have is closed nested flux surfaces. Because if the flux surfaces are not nested, so if the magnetic field is not wrapped on surfaces that nest one inside another, then it's going to start drifting out of the machine and your particles can flow along the magnetic field and just get lost, okay? So that's what this figure shows. It shows several flux surfaces that are cut out so you can see what they are, but they're all nested one inside another. Okay. So back to the how can you get the field lines to wrap around the rings. The first method that I told you about is running a current, and so this figure here shows a diagram of one such device. It's called a tokamak, sorry, and it has a symmetry axis is over here, and the current is running into the board and out and coming back through the other half of the machine that I didn't draw. And so, thanks to that current, there's a magnetic field that's created that goes around these surfaces like this. Okay, so there are two components to the magnetic field: a component that goes along the ring and a component that wraps it around the ring. So that's exactly what you want. And the problem with that is that this toroidal current needs to be quite high. It turns out in particular one of the reasons is that it gives you better confinement if the current is high. And in present-day machines, you use many mega amps of current. And this running such a high current through a plasma makes it very unstable. And what happens is that the whole plasma can become kinked and start flying into the walls and hitting the walls. And since it's very, very hot, 10 keV plasma, it has a very high current. The current starts going through the walls. It creates J cross B forces on the walls and can do a lot of damage to the vessel. It's not dangerous for anybody outside of the vessel, but it basically will destroy the machine. So ever since this device was invented, people have looked for other ways where you could have good flux surfaces and not strong plasma current. And that takes me to the second big idea in the magnetic confinement, and that's stellarators. So the idea in stellarators is instead of using current running through the plasma, you use current running outside the plasma to twist the column of plasma. And the twist forces the magnetic fields to go around and wrap themselves around the flux surfaces in the way that you want. Okay, and so that's what's shown by these two figures. The top figure shows what the machine actually looks like on the inside, and you can imagine that it's very difficult to engineer a machine like that. But it's become a lot easier because of computing advances. So now computers can run hundreds, thousands of optimization studies to see what's the best way to position the coils. And that field is growing rapidly. With heaven knows, with quantum computers, they'll probably do amazing things. But okay, and then and the bottom figure just shows one such plasma, and so you can see how how strongly shaped it is, and how the field lines sort of have to go around this flux surface. Okay. Right, but there's some serious questions, as you can well imagine, with the nature of this 3D equilibrium and what a plasma does once it's put into such a complicated structure, and that's what I'm going to be talking about in this talk. Okay. So, magnetic geometry. So, a little bit of math here. This is the slide that has the most math in the whole talk, so you can relax after this one. So basically what you want is to have force balance. So the product of the current and magnetic field has to balance, which is basically the Lorentz forces, have to balance the pressure forces, the grad P. And you can use that to solve for the perpendicular, the perpendicular part of the current in terms of the pressure. And so that, once you know the perpendicular part of the current, you say, well, wait a minute, the divergence of the current has to be zero because my charges isn't getting lost or created anywhere. And so from that, I should be able to determine the parallel component of the current. And that's given by this equation. And you can solve this equation. It just says that the gradient along the field line of the parallel current is driven, if you like, by this source-like term, which is the divergence of the perpendicular current. So you solve that equation, and you find that it's a little bit like the equation for the motions of particles and accelerators. There's a resonance. Every field line that closes around the machine by going a rational number of long rotations and a rational number divided by short rotations, okay? So if the field line closes upon itself, that's really what I'm trying to say. If it closes upon itself after going around the machine for a few times, then that field line is going to have a resonant response to this perpendicular current. And when you solve this equation, the parallel current goes to infinity near these surfaces that have closed field lines on them. And that's shown by this denominator here. So M is the number of times, it's a harmonic. So you're solving for the harmonics of the Fourier harmonics of the current. And this gives you the poloidal, so the harmonic number in this direction, and N gives you the harmonic number into the board. And when the ratio of those two numbers is equal to the winding number of the field line on the surface, then this denominator vanishes and your parallel current is infinite. Okay, so that's not physical. So how are they resolved? What happens if you try to do something like that? Well, one of the ideas in the early days, in the 50s, was, well, the way to avoid that is you don't have a current, you don't have a pressure gradient, right? It's the pressure gradient that drives this perpendicular current that's at the source of the whole problem. So if you have a pressure profile that's sort of like this devil's staircase, the pressure gradient in this function is zero almost everywhere. It just has a dense set of jumps. Then you won't have that problem. You won't have any of these singularities. And so that's obviously not sort of a mathematician's solution to the problem, and we expect that in the present. So for example, all of these jumps in pressures have to be balanced by infinite current sheets in order to satisfy the equilibrium force, to the equilibrium equation. And so, right, so the jumps in the pressure have to be accompanied by jumps in the winding number corresponding to current sheets. The current sheets will give rise to ohmic dissipation. The plasma is resistive. And the ohmic dissipation is going to give rise to magnetic reconnection, which is a way for the magnetic field to rearrange itself and do what it wants to do. And so the only way to avoid these singularities is to abandon the singly nested flux surfaces. And that's what nature does by itself. And that's where magnetic islands come in. So to study magnetic islands, it's good to remember that magnetic field lines constitute a Hamiltonian dynamical system, and you can see that I sort of simplified. In 3D, it's a little bit complicated. But in 2D, if you imagine that there's a dominant field going straight down the room, then in the cross-section plane, the magnetic field is described by this. So you can see that this flux function psi there, which describes the surfaces that the magnetic field wraps around, this flux function psi plays the role of a Hamiltonian. It's essentially a Hamiltonian. And so, so you can use all of the theory of Hamiltonian dynamics to study magnetic field lines. Oh, sorry, and in particular, one of the tools that will be important for us is the Poincaré diagram. So the idea of Poincaré is, in order to get to visualize what's happening to these to 3D trajectories, in his case, that are following some complicated dynamics, you can do a return map. So you only plot the intersection of your trajectory with some surface. You take some surface that you're going to use as your reference surface, this blue surface here, and every time the field line comes back and hits it, you mark a dot. Okay, and I'm going to be showing you a lot of this Poincaré sections, as they're called, And from these Poincaré sections, you'll see that you can have a pretty good idea of what's happening with a magnetic field. All right, okay. So here's the first one. So the first thing that happens is that you find that it's very easy when you have these surfaces where the field lines close upon themselves. Any perturbation will very rapidly give rise to magnetic islands, and there are these structures here. Okay, and the shape of the perturbation is shown here. So that is the way to avoid these current singularities. Basically, the only thing you can do is either you have a delta function where the field jumps, and therefore the current is a delta function at this resonant surface where all the field lines close, or you have to allow for them to form these, if you like, these little toruses who are, toruses on their own account. They're not, okay. The problem with those is that if you have only one of these resonant island chains, then it's fine. You've got good flux surfaces, as I was showing here. You see this is still, you have reasonably good transport throughout most of the machine. But if you have two chains like that, and they're close enough that the islands overlap, then the trajectory of the field lines becomes chaotic. And that's what's shown here. So I have one chain which has an m equals 4, and one chain that has an m equals 3, so 3 periods and 4 periods. And you can see that they create a lot of satellite islands, and the magnetic field lines become chaotic. And this chaos allows heat and particles to cross the broken flux surfaces, because there are some field lines actually, right, that start over here and will slowly drift across this noisy thing here until they get to the other end. So basically there's very poor heat confinement or particle confinement in that chaotic region. And this transport can easily exceed the transport caused by collisions, which is another way to move particles across the machine. So yeah, this is shown again here. So what happens with an island is that instead of flowing straight across flux surfaces through collisions like it normally would, the heat can now just flow along the field line and then jump a much shorter distance here and then flow back out. So there's sort of the island short circuits the confinement region in the plasma, basically. And this is shown in an actual experiment here that shows the electron temperature as a function of the major radius and time. And the time, you can think of the time basically as playing the role of the angle around the machine, because this island is rotating around the machine, and so time just allows you to see it at different angles. And you can see that the temperature profile is flattened here, and that's where the island is. So how can we predict how big these islands are going to be, when they're going to overlap, and when they're not going to overlap? And so that's the goal of the rest of the talk. One of the paradigms that I find helpful for bringing magnetic islands to life and often for understanding what's going on is comparing them to a ship. So you can see even from the previous picture, they sort of look a little bit like the keel of a ship. And the plasma typically flows. So for example, I mentioned that there's current flowing in the plasma, so that tells you that the electrons and the ions have velocities that are not equal. And this flow typically is going to be along the flux surfaces. So the electrons and the ions are going to be flowing at different velocities along these lines that you see there. And you can see that obviously when there's an obstacle like an island that's put in their path, that means their velocity has to change. The ion velocity, electron velocity, they have to deflect around these surfaces. Just in the same way that water and wind have to deflect when they come across the boat. So that's the first analogy. You can think of the electrons as being like the wind, and the ions being like the water, in the sense that the ions are much heavier and denser. The goal of the theory then is to provide expressions for the lift and the drag from the combination of the keel and the sail. The sail acts more or less like the wing of an airplane. It exerts force on the boat by changing the momentum of the wind, and it does so by creating circulation. So if you integrate the velocity around the wing, you get non-zero result, okay? And so ideal fluids, you have something called the Kelvin circulation theorem, which tells you that the circulation of the velocity around a closed contour has to be constant, and there's something similar in ideal MHD, which is that the flux has to be conserved. So there's analogies between the neutral fluid and the plasma. Another analogy is the sailboat couples two waves. It couples, you can think of the sail as creating a wave in the sense that there's a shadow of the wave, like the wind is perturbed behind the wave. And so if you're static, you'll see, and you look at the pattern moving, it basically looks like a wave in the wind that's moving across. So there's the wave in the wind, and the wave, of course, in the water, which you can see much more easily. You can see here that the boat sort of creates a hole for itself as it's moving along, and it creates a bow wave there. And one of the effects there that's going to be relevant to magnetic islands is that because of the bow wave, the ship is constantly sort of cruising uphill. Okay, the water in front of it is a little bit higher than the water in the middle of it. And if the wind is strong enough, it's possible for the ship to pop above that and to basically be gliding on top of the water instead of being in this little hollow here. Okay, and that's something that also happens for magnetic islands, as I will show you. Okay, so back to... so the lift and the drag, now I'm back to magnetic islands and showing you how they can be measured in practice. And so one thing you can do is look at the square root of the field perturbation and how that changes with time. And you do that simply by putting a little magnetic loop next to the plasma, and you monitor the current and the voltage in your loop. And that tells you the intensity, once you pick the right harmonic, it tells you the intensity of your perturbation created by a magnetic island. And so you see what's happening here is that, right, and the square root of the perturbation gives you the size of the magnetic island. And so what happens is that at some point, an island is destabilized and it starts growing. The derivative with respect to time is positive, it starts growing, and then it grows up until it reaches a higher amplitude, and then it just saturates there. Okay, and the figure below shows an island being dragged through the plasma. You can do that by taking some windings on wrapping some windings on the outside of your machine, and you run some current, some alternating current through that. And you can create a magnetic perturbation that basically catches the island sort of like tweezers and forces it to rotate around. And so that's what's being done there. And you can see that over here, the island velocity is different from the velocity of your tweezers, if you like. But at some point it locks, the two lock, and the island frequency goes up with the frequency of the perturbation. And the ion velocity goes up too. This is not a very impressive, perhaps, illustration because it's not a small tokamak, so there's a lot of noise, but it's a lot less noisy when you look at bigger tokamaks. Okay. Right, so this thing shows the amplification, which I call the lift, okay, this derivative here, and then the tendency of the island to lock onto the external perturbation gives you a measure of the drag. So there are two, what we've seen is that there are two or more states, right? What we had here, there's a small amplitude state and there's a big amplitude state there. And it's similar here, you have the unlocked state and the locked state. And that's confirmed by numerical simulations and by theory. And that's what I call the suppressed and the fulfilled islands. So in the left-hand side, I'm showing you a numerical simulation of a helical plasma state. So this is a tokamak in which you put a helical coils in order to try to make it into a little stellarator, if you like. And because the rotation was sufficiently large, the islands are not allowed to open. And what you have is just these twisted flux surfaces, but that don't actually open up islands. But what prevents the islands from opening is the rotation. And so if the islands are acting, the suppressed islands, these thin islands are exerting a drag on the rotation, it's possible at some point, if the rotation drive is not strong enough, The rotation just stops, and at that point the islands can open, and that's what's shown in this figure. So this the x-axis psi A shows the amplitude of the perturbation that's applied, and the y-axis shows the width of the island, and you can see that there's a bifurcation here. At the beginning, the perturbation is not strong enough to stop the plasma flow, and the amplitude of the island is very small. And then here, suddenly the plasma stops rotating, and the island is able to grow, and it reaches its fulfilled state. And this other curve here shows what happens if there's no rotation at all. Okay, and once the island is fulfilled, it tends to overlap with other islands, and you have this phenomena that I described to you earlier. The island overlap creates chaos, and you can see that in the Poincaré plot, where there's all these dots sort of all over the place. So one way of conceptualizing how to study this is by imagining that you can, what you're doing with the islands in a way is a little bit the same as what's done with ships in order to study the hydrodynamics of the ship, okay? So what you do is you put the ship in a canal and you force the water through it, and that way you can control the flow of water, and you can measure directly the force that the water is acting on the ship, the buoyancy force. And so this is basically what the simulations that we do try to do. We fix the flow. In the next few slides, I'll be showing you simulation where you fix the amplitude of the flow, and you try to see what its effect on the island is. And the top figure here shows the velocity of the flow. So this is actually, the top figure is now a plasma simulation, and it shows the velocity of the flow as a function of the distance across the channel when a magnetic perturbation is resonant here in the center. And so you see that when the flow is not going so fast, it's pinned. Okay, it's zero. The island forces it to forces the plasma to come to a halt at the center. Whereas when the flow is going very fast, the velocity does not go to zero, and so that's the state where the boat is popping on top of the water, okay? So this is basically your island surfing on top of the water, and this is an island that's sort of struggling to go up its bow wave. Okay. So I'm not going to so I've spoken mostly about the transition. I'm going to go a little bit more into details into the two states, the suppressed state and the fulfilled state, in particular with the interest being, you know, how big are the islands and what are the parameter regimes where these states can be realized or avoided. And so this shows you an actual experiment here where the most interesting tracks to look at are this second one here labeled airfield coil current and the rotation. Where did it go? Okay, let's look first at the rotation is all the way at the bottom. And so you see what happens is as the airfield again is this winding, this coil that's wound around the plasma to create a 3D perturbation, a 3D helical perturbation. As it's increased, and of course one of the interests in this is that tokamaks aren't perfect, and even when you don't deliberately put on such a coil, the coils that you put on to create your field are not perfectly aligned, and so there usually is a little bit of a helical perturbation that's present there whether you want it or not. And so that's why they're called airfields. Okay, so this airfield is increased in steps to see what it does. And you see that on this last, no, the one before last step here, suddenly the rotation plummets. And so what happens there is there's no longer an equilibrium between the drag that's applied by the magnetic resonance and the torque that's put on the flow by the plasma is basically, the plasma rotation is driven. And the equilibrium is lost, so the plasma stops rotating. And you see what happens there is at the same time, the amplitude of the perturbation, this thing that was I labeled By in a previous graph, suddenly starts jumping. That's what you see here. Okay, so this is the magnetic perturbation measured at the outside of the plasma, and you see that it starts growing. And then over here, the airfield is just turned off. The current in the airfield coil is turned off. And so this island that has grown now is no longer locked to a particular field, and so it starts being entrained by the plasma, and it starts rotating. And so this little wiggle that you see there is the island suddenly accelerating and rotating around the machine, okay? So that shows you that what this increase, this change in the magnetic field measured at the outside was caused by is this island that's now rotating, and then of course it eventually goes away since it doesn't have an airfield driving it anymore. Okay, in simulations, this shows simulations of what happens during mode penetration. So there's a magnetic resonance here in the middle, and the colors show the vorticity of the plasma. And it's the ion vorticity. And there's a band, so one of the aspects that I mentioned was important with ships is that there are these waves there that the perturbation couples to. And so here the island also couples to something called drift waves, which is sort of a variant of a sound wave. And if you know about Rossby waves in the magnetospheres, that's basically drift waves is a plasma version of a Rossby wave. And so depending on the plasma velocity, the Rossby waves can be cut off. That is, there's no possibility for propagation. The roots of the dispersion relation are complex, so they're just attenuated. But when you change the rotation of the plasma, you can get to certain characteristic frequencies where these waves are not cut off anymore, and that's shown by this middle slide here. And so you can see there that the perturbation is starting to couple to the plasma, and it's creating these little vortices. And then when you go further, now you're in the regime where the waves can propagate, and the island, or the resonant perturbation here in the middle, is actually exciting this wake field that's traveling out. Now, in practice, there are some damping mechanisms that were not included in this simulation, so these waves are not going to go undamped all the way to the edge of the box like they do in the simulation. But this is an important mechanism, and one of the things that you expect it to do is it creates a lot of energy to create that wave. So you would expect that to be stabilizing, and I will show you that that's indeed the case. So the creation of these waves sort of saps energy out of the magnetic island. So this is another type of simulation. The previous simulation was using a fluid code, and this simulation uses what's called the gyrokinetic code, and it shows again that as you apply so ignore these, I'm not going to cover these, I'm just going to focus on these. So this is the magnetic perturbation, the amplitude of the magnetic perturbation outside the plasma, and as the air field is applied, at first the island is grabbed by the magnetic field, and so it changes phase, and that's why, right, you can see that the real and the imaginary part change a little bit. And then as this air field as the rotation is increased, at some point the rotation of the plasma, the torque exerted, the force exerted, the drag force exerted by the plasma on the island is too great, and the plasma basically rips the island away from the perturbation that it's anchored to. And so the island starts rotating. And so this is basically the equivalent of, where was it? Of this oscillation that I was showing you here. So here's an island that's spun free, and this is the numerical equivalent of an island that's spun free. Okay. There's an analogy between the response of the plasma to these resonant magnetic perturbation and the rings around Saturn. So the the rings around Saturn are caused by ice. It's basically ice orbiting Saturn. But you might ask yourself, why is this ice not distributed homogeneously? And indeed, if you distributed it homogeneously and there was no interaction between the different icicles, they would just stay there and it would stay homogeneous. And so the important point of commonality with the plasma case is that it's a collective phenomenon. There's a role played by collisions and waves in clearing certain orbits of ice particles, which is what gives the rings this groovy aspect that is familiar. Okay, so that's it for the suppressed islands, and now I'm going to talk a little bit about the fulfilled islands. So what happens if an island is allowed to grow to its sort of natural amplitude? So the first thing you find is that, as I mentioned, the plasma now has to go around these big fat islands, and as it goes around, it has to accelerate. So this acceleration causes a force, and the forces causes current, and the current itself has an effect on the size of the island. So there's a lot of interest in being able to calculate exactly the magnitude and the sign of that effect to see when it could be stabilizing or destabilizing, and that's what I'm going to be talking about in the next couple of slides. So the one thing that analytic calculations find is that this lift function that I was telling you about, the thing that makes the island grow or shrink, is proportional to the product of the velocity of the plasma with respect to the island times, and this is the velocity minus the ion derivative. So basically it's proportional to the square of the velocity. And that's actually can be explained in terms of the proportionality to the product of the flux. So the amount of plasma that's going past the island is already proportional to the velocity. That gives you one of the V's. And then the captured momentum, the change in the momentum is also proportional in V. So that gives you the other factor of V. And that's where the factor of V squared comes from. And it's exactly the same argument that as was used by Newton in probably the first history, the first explanation of lift in the history of science. So the expression for this lift caused by it's called polarization effect, may be viewed also as a plasma version of the Kota-Joukowski theorem. The Kota-Joukowski theorem says that the lift on an airfoil is proportional to the product of the velocity times the circulation, and the circulation again is proportional to the velocity. Okay, so there's again the analogy between boats or airfoils, if you like, and islands. The problem, though, is I haven't told you what the velocity is, and it turns out that that's a very difficult problem to solve. In fact, it's not completely solved. So we don't really know how to calculate if you don't grab an island by tweezers and you just let it do its own thing, how quickly is it going to rotate, and therefore, how big is this term going to be? And so we started doing that in some simple models, and this shows the result of some fluid simulations. And the the top upper figure shows the island rotation frequency, so the frequency as it goes around the tokamak, as a function of its size. And so what we did is like these water tunnel things where you put a boat in the water. So we put an island in the plasma, and we looked at how the rotation, we let the island come into rest with its surrounding plasma to see what its natural propagation velocity is going to be. And what we find is that as the island grows, the natural rotation velocity goes from 1, which is the velocity of the electrons, and it slowly decays until it goes to 0, which in this normalization is the velocity of the ions. And that's not so surprising when the island is very thin. The electrons have a very small gyro radius, so they will be frozen in the island even if the island is very thin. Whereas the ions have a much larger gyro radius, so they tend to average out to not even see the island if the island is too thin. But as the island grows and its width becomes comparable to the radius described by the ions in their rotation, then the ions become also frozen into the island, and they force the island to lock. Okay. And the most interesting thing with this, perhaps, is the effect of this on the lift, and that's what's shown in the lower figure here. So this G is proportional to the lift I was telling you about. And what's found is that there's the lift is strongly negative. So this effect of the plasma flowing past the island is very stabilizing, and it's most stabilizing when the island is of such a size that it couples very strongly to the sound waves. And that's what's shown by that's why we have two figures here. The black and the pink curves correspond to different magnetic shear, and changing the magnetic shear and the density scale length changes the size at which the island couples to the sound wave. And so what this really shows is that when the island couples to the sound wave, it takes a lot of energy for it to excite this wake, basically, that it's dragging around itself. And this energy has a stabilizing effect so that the island has a tendency to shrink. So we've now seen that there are basically two stabilization effects against magnetic island. First is the rotation itself. If you try to insert an island rotating at the wrong velocity, the plasma just won't allow it. And that's this bifurcation mechanism that we saw at in the suppressed island part of the talk. And then even if somehow the island manages to lock the plasma rotation so that they're in agreement, so to speak, with each other, there is still this effect, the stabilizing effect of the inertia of the ions flowing around the island. So this brings me to my summary. So the helical approach to magnetic confinement offers the promise of disruption-free operation, and that's very important. Suppressing magnetic islands is thus the key to the success of the helical approach. So the price you pay for getting rid of disruptions is the possibility of magnetic chaos throughout your confinement device, and therefore having very bad confinement. So you have to get rid of the islands, and I've shown two ways whereby, two sort of stabilizing effects that help you get rid of islands. And these stabilizing effects have not really been so when I was telling you earlier that accelerators are designed by these massive optimization studies where they run thousands of different equilibria. So these 1,000 different equilibria in the stellarators that currently exist, they were designed without taking into account the effect of rotation. So there's a possibility that by looking at this effect of rotation in future designs, we'll be able to have a much wider operating space and design better stellarators, basically. So the plasma flow offers a margin of safety by suppressing small magnetic islands. In axisymmetric devices, so like tokamaks, suppressed islands can have a beneficial effect on stability by tailoring plasma rotation and pressure. So I haven't talked about that very much, but even if you have a machine that's nominally axisymmetric, it can be advantageous to put a very little resonant perturbation to slow down the plasma rotation if it's going too fast somewhere where you don't want it to go fast, or to reduce a little bit the pressure gradient. And that's something that's also an area of active study. The islands are unfortunately often too small for direct observation, and of course the plasma is very hot, so you can't put anything in the plasma, it would just vaporize. So the only thing you can do is look at waves that are coming out, like RF or electron cyclotron waves, etc. So that what you have to do to diagnose whether the island is there or not is look at when it changes, because when it changes, then you see something happening on the outside, and that's your sign that something has changed. Okay, and there remain many interesting problems, such as the role of the island wake. It's not completely understood yet. The interaction of islands with turbulence. All the simulations I showed you were in quiescent plasmas. There is no such thing as a quiescent plasma. It's a theorist's a figment. I shouldn't say it was in quiescent plasma. It's in plasma where you replace the turbulence by anomalous diffusion coefficients, anomalous viscosity, anomalous everything, okay? But it's otherwise quiescent. So the turbulence, the interaction of the turbulence with the islands is only now starting to be looked at. And the scale lengths actually of the turbulent vortices in plasma and islands are comparable. So this is very much something that needs to be looked at. And then finally, the role of kinetic islands, collisions, and the fact that particles, have long mean-free paths. That's something that's also starting to be looked at. And that's all. Thank you.